Hi, my name is Alessandro Gabori. I'm CEO at Lithium Lasers. Thanks for your interest in my presentation about new compact and cost-effective high-power femtosecond lasers emitting high-quality femtosecond pulses. Lithium Lasers design manufactures ultra-short pulse laser for scientific and industrial applications. Many research applications in the field of biology, non-linear optics, and material processing can currently benefit from our technology. Our ambitious goal is also to bring strong innovation in industrial material processing field by developing an innovative laser system for speeding up micromachining processes. I will briefly discuss about this project later. Let me introduce our company first. Lithium Lasers is a spin-off of Politecnico of Milano, founded in 2019. Our team is a combination between industry and research skills, and we mix the scientific experience in the field of spectroscopy and neuroscience with a solid background in ultra-fast laser industry. Our production facility is located close to the mountains in the Trentino region. All our lasers are based on a unique solid-state optomechanical platform that is specifically designed for high-power ultra-short pulse lasers. Many different laser systems can be realized based upon our optomechanical platform to reach specific cutting-edge performances with a lean and robust laser architecture. Our platform brings many advantages in terms of laser performances and features that are highly relevant in many scientific and industrial applications. The aim of a femtosecond laser is to concentrate light into a very small packet and do it reliably. The idea of femtosecond laser should provide laser pulses without leaving any photons between one pulse and one another, and thus it should exhibit minimal noise. Thanks to our optomechanical platform, our lasers exhibit ultra-low noise, and here in a typical relative intensity noise measurement, like the one here reported, a shot noise level of minus 150 dB per hertz is reached above 1 megahertz. Our lasers emit ultra-short soliton pulses with perfect spatial beam properties, even at very high power levels, and complete absence of satellite pulses or pedestals. The pedestals are the small lateral pulses that you can see in some autocorrelation traces. Pedestals affect the peak intensity and decrease the nonlinear interaction efficiency. Our lasers have no pedestals, and therefore they improve the peak intensity and efficiency in nonlinear interactions. Our lasers also exhibit exceptional long-term average power stability with an RMS noise less than 0.1%. Thanks to our optomechanical platform, we managed to integrate control electronics and laser head in only one tiny box of 300 times 400 millimeters in size and only 8 kilos in weight. We can provide a small footprint as compared to other lasers that consists of 2 separate boxes for the laser head and for the controller. So if you want to avoid bulky laser systems, our laser is really convenient because it is built in a single enclosure solution. The platform has been designed to provide reliable system with long-lasting performances to the industry. All our lasers are subjected to harsh environmental and mechanical stress tests before being released to the customer. Based on this platform, we developed Lithium Six, a family of high-power power lasers emitting femtosecond pulses at a breakthrough price. Lithium Six is available in 2 versions, with central wavelength in the near IR region and in the green one. The near IR version provides several fixed wavelengths ranging from 1030 nanometers to 1070 nanometers. Pulse duration from 120 to 180 femtosecond, average power between 3 and 10 watt, and pulse energy from 37 up to 125 nanojoule. The green version of the laser provides several fixed wavelengths in a range from 515 to 535 nanometers, pulse duration from 130 to 200 femtosecond, average power between 1.5 and 5 volts, and pulse energy from 18 to 62 nanometers. Each version offers several repetition rates in the range from 40 MHz up to 220 MHz for experimental optimization, and they can be fitted with AOM for fast power control. Lithium Six can also be fitted with an optional nonlinear conversion module for broadband output generation. This module is based on an LMA PCF fiber that converts the narrow band high peak power pulse into a high power broadband output with wavelength ranging from 950 to 1200 nanometers. Lithium Six Broadband broadband exhibit low noise broadband signal output and temporally and spatially overlap multicolor pulses. This is a new laser system and is suitable for multiplex or broadband coherent Raman microscopy. Here we report laser specifications that show bandwidth up to 260 nanometers, pulse duration less than 200 femtosecond, average power up to 5 volt, and repetition rate of 80 megahertz. I would like to show you some example of what the Lithium Six laser is suitable for. These are two photon fluorescences of pollen grains obtained using the infrared version of the laser called Lithium 61050. In this example from the IIT of Genoa, Lithium 61050 is used in vivo two-photon function imaging of neural activity in the deep somatosensory cortex. You can appreciate the calcium changes recorded from 3 neurons at a remarkable depth of 540 microns. With Lithium 6, you can choose the fixed wavelength that best suits your experiment. 1050 is a good wavelength to excite the majority of redshifted calcium indicator. However, when you want to combine functional imaging with optogenetic stimulation, a red-shifted wavelength is preferred to minimize crosstalk between imaging and photostimulation. Our Lithium 6, in its 1070 nanometer version, offers the more redshifted fixed wavelength on the market. By choosing Lithium 6 at 1050 nanometer, you will decrease the crosstalk between the imaging laser and the opsin activation. On the contrary, if you perform an experiment of dual color imaging with a yellow calcium indicator, you will prefer to choose the Lithium 6 version with fixed wavelength at 1030 nanometers. Flexible wavelength can therefore help you in the optimization of your imaging experiment. As previously introduced, we are currently working on an innovative laser system for industrial material processing applications. The main challenge of micromachining is to combine precision and speed. Indeed, microsecond, nanosecond pulse lasers are fast at machining, but pretty imprecise. Whereas traditional ultrashort pulse laser can machine very precisely at fairly low speed. At Lithium Lasers, we are currently developing an innovative high-frequency burst mode laser that will be able to combine speed and precision in micromachining applications. Our laser will emit bursts of many high-frequency pulses that are slightly above the material machining energy threshold. When this burst of pulses impinges onto the material, they enable efficient material removal, minimizing spurious side effects such as plasma shielding and micro cracks. Our laser will have average power in the order of tens of watts, wavelength in the near IR and green region. The pulses within each burst will have a repetition rate in the gigahertz range, and the number of pulses will be adjustable from 50 to 1000. In order to optimize the laser operation upon micromachining process of different materials, the burst shape will be also controllable via software. We are looking for partners, for laser integrators, researchers who would like to test our laser or discuss about our new exciting micromachining project. Please contact myself directly or visit our booth and chat with us. Thank you very much for your attention, and I'll be open for questions on the chat box. Thank you very much.